we're not going to do that question over and over again. Okay, so continuity. So have you, before this class, heard of continuous functions?
Yes.
Maybe. Okay, so what is your general sense of what it means to be a continuous function? There's no, so we'll see if I can actually write a complete sentence, which is not a guarantee. So a function is continuous, which I'm going to abbreviate CTS just to save myself some time. If it has, what would you say? How about, would you agree with the no breaks? Does that make sense? Or the way that it was explained to me the first time is if you can draw it in one continuous go without lifting your pencil. Have you seen that before too?
Yeah.
Okay. So with that definition, would lines be continuous?
Yes.
Yes. How about parabolas?
Yes.
How about things like 1 over x? No, that wouldn't be continuous. Okay, so that is the layman's definition on your idea of what continuity should mean in your head. This is the technical definition using limits. And you're going to have to know this. I promise I'll put this on the quiz, and I'm going to give you 3 blanks. I'm going to say fill in what those 3 things are. It really makes me angry when I tell students that and they still get it wrong. Okay, so like you need to know these things. And it's kind of like memorizing my Russian vocabulary. I just have to memorize it. So technically, the way to say a function is continuous with limits is if the limit as x goes to a of f of x equals f of a. So what this is saying is that you can just plug a into f. And being able to do that involves sort of like 3 other things happening in the background. And the first thing is that f of a must be defined. And that's math speak. What that means is that you must be able to plug a in. And the kinds of numbers that you couldn't plug into a function are things that might result in, say, division by 0. Does that idea make sense? Okay. What this would look like in a picture, if it was, so number 1's picture, this is an example of a function where a is not defined. I mean, that's like so close to being able to draw it in one straight go, right? Except for you have to hop over that one little hole there, and that means it's broken. And you see how that means f of a is not defined. There's no number that's been plugged in for a, there's just a hole there.
What if there was a value though?
We'll get there. Yep, we'll get there. Question, so part 2, it says the limit has to exist in the first place. And so what this means is, or how this could not happen, is you could have something like that. Obviously that's not continuous, right? And the problem there is that the limit as x goes to a of f of x does not exist. And that limit doesn't exist because the limits don't match from the left and right side. The limit could also not exist by being infinite because technically limits that equal infinity, like that also. Does that make sense? That kind of is broken for 2 reasons. Reason 1 is you can't plug a, and reason 2 is the limit doesn't exist either. Okay? And I think number 3 is getting at the question that Jimmy was asking. He said, okay, well, what if that there is a number filled in there? So number 1 is uber close to being continuous, right? And if I was just smart and filled in that hole correctly, well, then it would be continuous. But what if I was stupid and I filled in the hole up there? Is it continuous now?
Yeah.
It's still not, right? And the technical reason is, shoot, I made a boo-boo. This should say not equal to. So say that was 3, and say this is 5. In that little picture I drew, what is the limit as x goes to a of my function? 3. And what do I get when I actually plug in a? 5. And notice how those 2 things are unequal. So the limit exists, the function is defined, but you didn't fill in the hole correctly. And that's a problem. So those are the three ways a function can fail to be continuous. I'm going to ask you to like list them, and I'm probably also going to give you a function and say, okay, which part of those three parts is wrong with this function? Does that make sense? So which of these three things is failing? And the pictures, I think, really help with the ideas of who's failing and what part's failing and what part's not.
What about the other ways, like the cusp or whatever it's called?
Oh, the cusp is something different. So we'll get to those when we talk about derivatives, but technically a function that's like this is continuous. It's not differentiable, and that's something we're going to discuss tomorrow.
Okay.
But it is still continuous. Yeah, bird functions are continuous. Flap, flap. So this really should have said equal. Yeah, I was phrasing it in terms of what it shouldn't be, and I don't know why yeah, that should say equals. I'm so sorry. Yeah, this has to happen. And that's the next picture of it not happening down below. Oh. Apparently I need more coffee. Thank you. Okay. So we have a graph of a function at which numbers is it discontinuous and which of those three reasons are why. You don't have to call them reasons. You don't have to list them in the same order as me. It's just from that list which ones. So first of all, where is this function discontinuous? At what numbers is it broken? 1, 3, and 5. Okay. So half of the question is figuring out where. Okay, so at x equals 1, what is the reason? Of those three we listed, which one is the problem? The whole. And say that in math speak, though. So that reason is f of a is not defined. This one is, f of 1 is not defined. Okay?
That's what a whole means.
That's what it, yep, that's what a whole would mean. That the function is not defined at that point. Meaning 1 cannot be plugged in. Okay, at 3 there is a break in the graph or some kind of jump. Which of those three reasons was it? The limit as x approaches 3 of your function does not exist. That's the reason it's broken. So that's what a jump is in math speak. The limit doesn't exist. Is f of 3 defined? Can you plug 3 in? Yeah, because this actually filled in down there. Okay, how about x equals 5? What's the problem there? Does the limit exist?
Yes,
Is it defined?
yes,
But,
they are not equal.
uh-huh. So the limit as x goes to 5 of your function is not equal to what you get when you input 5. Okay?
So in the previous rules, it should say equal?
Oh, in the previous rules, yes, it should say equal, shouldn't it? I thought I boo-booed and I didn't. Right, do you get those reasons? Okay. Now we're going to do the same thing, and we're going to do it with functions where we're not necessarily given a picture. You could sketch a picture, or you can just tell from the equation what's wrong sometimes. Like if you can't plug a number in, it's usually pretty evident from the equation itself. Okay, we good to go? Jim, you good to go? Okay. Okay, so explain why this function is discontinuous at a equals 1. So why is 1 problematic for this one? Yep. F of 1 is not defined. It also is the case that the limit as x goes to 1 of f of x technically does not exist. If you were to look at a picture of this function, it's this 1 over x squared function, which looks like this, moved over 1 and then reflected over the x-axis. And the limit doesn't go to a specific number there, it goes to negative infinity. That technically is not existing, because existing means the limit is a number. But the going to infinity of some sorts is not existing in a specific manner. Does that make sense? Okay. So those are the two reasons, but I mean, if I only ask for one reason, the first one's good enough. It's also the easiest one, right? You obviously can't plug one in. Okay. So this function, okay, can you plug -3 in?
No.
Technically you can, because it's a piecewise function. I said, okay, well my function is this all the time, right? Except for when x is -3, then I say, okay, well then it's -5. So technically you can plug -3 in. F of -3 equals -5, because I said so, okay?
So that's the point.
Yes, so that means that, so problem part number 1 is okay. It's been defined. So 1 is okay. For 2, we have to find the limit as x goes to -3 of this function. So is that something that you guys could now do? Yeah, so it's a pretty basic one, right? Factor. How does the numerator factor?
X minus 4x plus 3.
Great. And does the problematic denominator cancel?
Yes.
Yes, it does. Woohoo. Okay, and so what is that limit? I believe it's -7. Okay, so part 1's okay, the limit's defined, or the function's defined. Part 2's okay, the limit exists and it's -7. Which part is broken?
They're not equal.
Part 3, the limit as x goes to -3 of your function is not equal to get when you plug in -3. So this would be an example of a line with the hole filled in the wrong way. If you graph this function, you can graph x minus 4. It's a line with that kind of y-intercept and a hole in it. And then instead of being filled in at -7, it was filled in at -5, a little bit too far up. So what number could you have chosen here to make it continuous? What would you have picked to make it work? You need this to equal this, right? So what should I have put there to make the hole filled in correctly? If you would have put -7 there, it would have been filled in correctly and it would have been continuous. Does that make sense? Okay, but because it was not, that's part 3. Part 3 is the trickiest one to spot. If you can plug the number in and you can find the limit and those two things are not equal, that means you have a hole but it has not been filled in right. Okay. Couple more. How about this one? Where is this function discontinuous? At?
X equals 2.
Because f of 2 is undefined. Or you could say does not exist. That's the same thing. Yep, f of 2 is undefined / does not exist. Okay, how about b? Okay, 1 over x squared if x is not equal to 0 and 1. So technically, if there's going to be a problem point, where's it going to be?
At
At x
x equals 0.
equals 0. So at x equals 0. Is f of 0 defined? Can you plug 0 in? Yes. When I plug in 0, I said you get 1. This, as a picture, looks approximately like this. And then there's a dot there on that vertical asymptote. So does the limit exist? No. So the problem is that the limit as x goes to 0 of f of x does not exist. And you can't just make a point have like a value of infinity, so there's no way to fix that function.
So if
It's going to stay broken.
So if I say the limit doesn't equal the actual value.
That's also correct. Yeah, you could say that the limit as x goes to 0 of f of x is not equal to 1, because that limit is infinity, and infinity isn't equal to 1. So in this case, it's either reason number 2 or reason number 3. Both of them are completely legitimate things, and I would give you full credit for each. Yes?
Whenever there's more than one, do you want us to list all of the reasons?
If I would have to specify that, and I don't want to give you that much of a hint. So if there is more than one, I won't say that there's more than one. You only have to give one reason. Okay.
The reason would be correct.
Yeah, the second reason would also be correct. The limit does not equal the function value. They're both fine. Don't care which one you give. Yes?
Is it usually because there's an exception, like the top one piecewise, says x cannot equal 0? Is that like a hint that it's not continuous?
That doesn't necessarily mean it's not continuous because for this one it does. There's no way to make it happen, but in the previous one that was piecewise, if I would have put in the right number, it would have been continuous. Does that make sense? So if I wanted to make question part B of example 2 harder, I could have said, is this function continuous or not? And I could have filled in that number correctly. Does that make sense? So it is the case that some piecewise functions are continuous. And even ones you could think about having a square root and a line, if they were joined together correctly, if they matched up, then they'll be continuous. So the question is, how do you check and see if they match up? And we'll get to one of those. But the piece where they are put together is typically a good candidate for being broken. Okay, this function that's on your homework, I don't know how to make the notation quite right in my notes, but this is called the greatest integer function. I think a better name and a common name is called the floor function. It is a step function, but the thing is, a step function is a more general term that refers to all different kinds of functions. Because lots of functions can be step functions, but this one specifically is the round down function. Does that make sense? There's also a round up function. That's also a step function, but it steps in a different way. So what the floor function does is it takes the number and it rounds it down to the nearest whole number. So all the numbers between 0 and 1, what are they going to round down to? 0. 0 rounds down to 0. Everything up till 1 rounds down to 0. What's 1 going to round down to? Does it round at all? It's going to stay 1. And everything up until 2 will round down to 1. Does that make sense? And this stepping pattern is going to continue from 2 to 3, and then it jumps. Can you think of and it also happens with the negatives. Things like negative 0.9 round down to negative 1. Does that make sense? And it goes off in both directions forever and ever. So this function is discontinuous in lots of places, right? What would be a way to list them? At x equals, there's a name for all those places this function is discontinuous. The integers, x equals n, where n is an integer. I know nobody talks on their cell phones anymore because you just send text messages these days, but back when I had a cell phone, I would talk on my cell phone, and when you talk for 1 minute and 2 seconds, what does the cell phone company say you've talked for?
2 minutes.
So what function do they use? The ceiling function, the round up function. That's an example of how this could come up in your life, is stuff like that, where there are places that round up or always round down. So, okay, but the name floor is much, much clearer, at least to me, than the greatest integer name okay. Okay, so with this, okay, so a function is, you can be continuous from one side or the other. And we had a picture, we graphed this combination of sine and cosine, and it was discontinuous at pi, and on one number it was filled in, one side it was filled in and one side it wasn't, right? So this has to do with breaks in the graph where one side is filled in. So it's continuous from the right if you take the limit from the right and you have that side plugged in. So this would mean that in a broken function like this one you got a picture of, the right hole is filled in. What does the second one mean?
Left hole.
Left hole is filled in. So a picture of something continuous from the left would be something like that. As you come at the function from the left side, that's the hole that's filled in. Continuous from the right would look like this, right, the opposite. The right hole is filled in.
So this is just for this round down, round up.
It will, yep, and it will only be the case for functions that have a jump discontinuity, where there's some kind of break in the graph.
Oh, okay.
And the reason, we'll talk about that when we go example 4. So in example 4, is the function continuous from the left or right at -1? If you go to the, no, okay, so at x equals -1,
Could we have an open circle on the jump?
yes, well, I'll draw a picture of that, okay? How about at x equals 3? Continuous from left, right, or neither? From the left. So CTS from left. How about at x equals 5? Is the hole filled in from the left, from the right, or neither? Neither. So I think that Jimmy's question was, what would happen if you had a jump and neither hole was filled in? Is that what you were asking, Jimmy?
Yeah.
Okay, so in that picture, if the hole isn't filled in and from the left or from the right, it's not continuous from the left or right, also would be neither in that case. Could it be continuous from the left and right? Could I fill in both holes? No, because then it wouldn't be a function. If I filled in a hole like this, it's just gonna be continuous. Does that make sense? That's not from the left and the right, which means it's just continuous. So, though that kind of specific thing really only applies to functions where there's a jump.
If it's two solid dots, then it fails the one.
If it's two solid dots, it fails the vertical line test, then it's not a function. So you will never have both of those filled in unless it's something like this one, in which case you just say it's continuous. There's no need to specify the left or the right. But the specifying the left and the right lets you specify with these jump discontinuities which side of that hole is filled in, if any. Does that make sense? So being from the left means, okay, well on my left piece, that's the hole that's filled in. If it's from the right, on the right piece, that hole's filled in. Okay, that's what it's specifying. Woo, piecewise functions. Yeah, that's what you got next? Okay, so for x's that are less than 0, that means the x's that are equal to 0 or all the negative x's, you have a picture that is a parabola shifted up one. If you'd forgot what points that goes through, you can just plug numbers in, right? Plug in 0, you get 1. Plug in -1, you get 2. Plug in -2, you get 5. Okay. And the only reason I plug in negative numbers there is because that's only for x's that are less than 0. Right? X less than 0 means x is negative. Okay. How about 2 minus x? If you were graphing that, it's a line. What would its y-intercept be? 2. And is it clear that there's going to be an open circle there because I technically can't plug in 0? But I can plug in 0 to figure out where my open circle goes. Okay, what's the slope of this line? -1. So I go down 1, forwards 1. That's where x is 1. I go down 1, forwards 1 again. That's where x is 2, and that's where I stop. Does that make sense? Because only between 0 and 2. So I've got that little chunk of line. And how about that last piece? Okay. I can plug 2 in to figure out where my open circle goes. Does that make sense? When I plug 2 in, what do I get? 0. So that kind of has an open circle over that filled in circle. So they match up there. What would happen if you plugged in 3? 1. If you plugged in 4, you'd get 4. You're going to get that basic other half parabola shape. So is this function continuous at 2? Give me a nod or give me a shake. Is it continuous at 2? Yes, it is. Okay. Okay, so at which of the numbers is f continuous from the right, left, or neither? So is f is continuous from the right at any points? I don't think I see any, right? How about the left?
0.
At x equals 0.
So you wouldn't include the 2 because it's the open circle.
Well, it's an open circle from the parabola, but the line had it filled in. So since it was filled in by one of those functions, it's continuous there. So the function is continuous if x is not equal to 0, everywhere except for 0. Now here's a good question. What if I would have done 0 less than x less than 2 and left off the or equal to? How would that change the picture? If I leave off the or equal to, would this circle have been filled in by the blue line? No, I would have had 2 open circles there, which would have meant the function is actually discontinuous there as well. Does that make sense? But because one of them was filled in, you're good. Okay. Does that make sense? Alrighty. What would I have changed to make it continuous from the right at 0? What would have had to have changed in that piecewise definition? So it's from the left because the left side is filled in, right? So if I want it from the right, I've got to make the right side filled in. So what do I have to take away on this thing? The equal to, and what would I have to add into right there? And equal to. That's what determines which of those holes is filled in. Okay, the next question is nebulous, lots of right answers. So sketch a picture of a function that has a jump discontinuity at 2, meaning there's some kind of break where there's a distance between those two pieces, and a removable discontinuity. That's the same thing as saying there's a hole at x equals 4. Also, the function should be continuous from the right at x equals 2. Okay.
The removable is the dot.
Removable is the open circle. Yep, exactly. Open circle. Okay, there's x equals 1, 2, 3, 4. Okay. A jump discontinuity at 2, which means you have to have one low point and 1 point higher. They don't have to both be above the x-axis. That's just how I'm drawing them. Okay, so I've got something coming up that way, something going this way. I have to leave a hole at 4, and then I can do whatever the heck I want. If I want to oscillate, if I want to go wee, I can. Doesn't matter.
Removal discontinuity, the limits have to agree.
Yep. Removal discontinuity means that you could remove the discontinuity by just filling the circle in. Does that make sense? Like, it can be removed if I were to just fill in that dot. Versus like that jump discontinuity, I can't fill in the dot to make it go away. Okay, and if it's continuous from the right, which of the dots at 2 is filled in, the lower dot or upper dot? The upper dot is. And there's lots of things that says, like that one is one answer. There's nothing that says your function couldn't have, say, done something super, super wacky. It could have done that kind of thing as well, like that has the same properties, right? It's still, there's still going to be a crazy jump at 2, right? But the right side is filled in. So, I mean, there's lots of answers that are correct, and the way this is asked in WebAssign is they give you a bunch of possibilities. You have to figure out which one meets those criteria. Okay, awesome. Now, these functions are continuous at every number in their domains, which means if you find the domain, you know where the function is continuous. So this is another way for me to rephrase those questions that I asked in the first, in one of the chapter 1 review, is like find the domain of the function is the same question as saying where is this function continuous. And this is true for polynomials, root functions, rational functions, trig functions. I don't know why, but it's also true for log functions. And just think about, math only has 3 commandments so far, and that's the only thing I'm going to hear. You probably remember. So you can't divide by 0, you can't root negatives, and you can't log 0 or negatives. That's all you got to remember. Was that too fast? Don't divide by 0, don't root negatives, don't log 0 or negatives. Okay, those are the 3 commandments you got to remember. Thou shalt not. A student write that as a reason on their homework, and made me so happy. Okay, so on what intervals is each function continuous? So this guy is a polynomial, right? Are there any numbers that you can't 100th power or 37th power? No, so this is going to be continuous on the whole real number line, or you could say negative infinity to infinity. You don't know what it looks like specifically, but you know it's continuous. It's one smooth curve. Okay, in B, you have the potential to break mathematical commandments, right? And you got to make sure that the numbers that you plug in are okay in every single piece. So for this one, so for root x, x must be bigger than or equal to 0, right? So x bigger than or equal to 0 is a requirement, or you're breaking the thou shalt not root negatives. How about the second fraction? Is there a problem there? I think it just can't equal 1. Does that make sense? Yeah, anything except for 1. And how about the last part? Are there any problems from this guy?
No.
No. So if you tried to solve x squared plus 1 equals 0, you would get x squared equals negative 1, which means x is only can't be imaginary numbers, and we're working with real numbers, so imaginaries are, we don't care about them. Does that make sense? Say that again.
You said x squared plus 1 is 1.
Should have been 0, yes. Thank you. Okay, so we need to be positive, and x can't be 1. So take these two things and make them into an interval. So open or closed circle at 0. Well, closed. And what do you have to leave out? 1, union, 1 to infinity. Does that make sense? Okay. All right. How about sine? Is sine a function that causes problems?
No.
No. So is x squared something that causes problems?
No.
No. So in this case, the domain is negative infinity to infinity. All real numbers, no big deal. Okay, how about part B? Is there potential for problem? Yeah. That problem would occur when root of stuff equaled 0. Wherever that happens are numbers we must leave out. I think you are awfully close. You missed one. Yes, exactly. So add the 4. How do you undo the root? Square x squared plus 7 equals 16, right? Take away 7, x squared equals 9. And two numbers when squared give you 9, negative 3 and positive 3, right? So for the domain, x cannot equal both of those numbers. And I'm definitely going to ask for intervals on your test, so let's just practice writing them. What would that be as an interval?
Parentheses, negative 30 to negative 0, or negative infinity to negative 3.
Uh-huh.
Intersection, negative 3 to 3.
Uh-huh.
Intersection, 3 to infinity.
You meant to say union, but yes.
I always want to leave out the middle part.
Say that again.
I always leave out the middle part.
Yeah, you got it. Well, and what you can also think is as a number line, that's the whole number line with just negative 3 and 3 punched out. And so just think, okay, to go from there to there, I need 1, here to here, I need 2, there to there, I need 1. And actually, there's a pattern. If you leave out 2 numbers, how many intervals are you going to have? 3. Does that make sense? The number of subintervals you have is always 1 more than the number of points you leave out. Does that make sense? If you leave out 1 point, you've got 2 subintervals, right? Leave out 2 points, you've got 3. Leave out 3 points, you've got 4. So maybe that'll help you remember. It's, oh, okay, I need 1 more. Alrighty. And this thing we've already discussed, but your book stated it again. So this will kind of review the quiz question that I think may give you some of the trouble. Remember how I said with limits, as long as you're not breaking any rules, you can just plug the number in? That's what this says. It says that if you have a continuous function, this limit can move inside of the function. See what that happened here in this last thing. So you took the limit and moved it inside of the f function. And that works as long as your f is continuous at whatever number you get when you take that limit. And so I think question A is kind of similar to quiz-ish, right? And what this is basically saying is that that limit can go inside. So this is cosine of limit x goes to 0, x plus sine x. Can you plug 0 into x plus sine x? Yes. Gives you cosine of 0 plus 0, which is cosine of 0, which is 1. You don't have to show this step. What I really care that you get is that with limits, all you have, if you can plug the number in, you should do that. Does that make sense? And recognize that, okay, I'm not doing anything funky here. I can just plug that number in. So like going to -7 in part B would be an issue, but can you go to 9? Yes. So just plug 9 in. This is 7 plus root 9 over root 7 plus 9, which is, 10 over 4? Do you agree with that? I know reducing fractions is hard, but if you've got 2 even numbers, please divide by 2 on both top and bottom. It makes me so sad when you don't do that. 10 over 4 is, or 5 halves. I don't care if 5 halves or 2.5. Ooh, good point, WebAssign. WebAssign does not like 2.5. Bad. Don't put that in. I don't know why they harp on that so much in elementary school, because it's always like mixed numbers until you're like, your brains come out your ears, right? But WebAssign has a very good reason why that's ambiguous. Does 2.5, does it mean 2 plus a half, or does it mean 2 times a half?
2 plus a half.
It means 2 plus a half, right? But in math, the default symbol is times, right? So when you give 2.5, it can be confusing for people. Does that make sense? They really shouldn't use that. I know they use that notation because they want you to get a sense for how big numbers are relative to others. But that's why you don't ever give WebAssign to mixed fractions, mixed numbers.
Maybe they should teach kids to just automatically put a plus between it. Not that much extra.
No, I think that would be a great thing to do. It just would involve like a curriculum change across the country, which would be like massively awful to implement, and people would complain because they always do. And one more thing about WebAssign is that unless it asks for a decimal, it wants the exact answer. So for example, if you had a question and the answer was 1/3 and you gave it 0.333, it's going to tell you that you're wrong. Does that make sense? So always give the exact answer. If you have to round anything and it's not asking you to round, don't round. With 1/2, it's okay to give 0.5 because that's exactly equal to. Does that make sense? But with 1/3 and 0.3, they're not exactly equal to each other. One's a rounded version of the other. Okay, there you go. Rant over. Next question. Alrighty. So we have this function, and I want you to be clever and make it continuous. So first of all, what are we putting together? What's the first function? What kind of shape is it? It's a line. The bottom function is a parabola. And if you want them to be continuous, they have to match. Does that make sense? In other words, the limit as x goes to 2 from the left of your function has to equal the limit as x goes to 2 from the right of your function.
I just got 6. I have to guess and check.
Okay, here's how you don't have to guess and check is by using this process, right? You could sort of guess and check and graph them and like find out what C's would make them match up. But if you use the limit definition, as you go at 2 from the left, which part of the function do you use? The top half or bottom half? Top. And as you go at 2 from the right, you use the bottom. And can you just plug in 2? Is there any funkiness going on?
No,
And does 2 go in for x or does it go in for c?
those are blanks.
Goes in for x. So I have 2c plus 7 equals 4c minus 5. Is it clear how I got 4 in that second half? How there's 4c there, does that make sense? Okay, and now can you solve that? Maybe you go back to your algebra 1 happy place and you're like, okay, I can add 5 to both sides and I get 2c plus 12 equals 4c, right?
C should be 6.
And 12 equals 2c, so c is 6. So the limits match up, so the limit exists. Technically, this does have to have that or equal to there for it to work. If there wasn't an or equal to there, the function wouldn't be defined. So the first thing you probably could say is like, f of 2 is defined. But I'm not going to be super picky about that because I want to just get you to get the basic idea that the left and right limits have to match.
You wouldn't give us one where you couldn't plug in, right?
No, exactly. And maybe you have to like do a little bit of math before you plug in, like simplify the limit some. I think the next example has that in it. So, oh no, it doesn't. But the one in your homework, when you find the limit, like if I'd given you like limit x goes to 2 of x squared minus 2, 4 over x minus 2, you could work that out by factoring and stuff. Okay, so this one is kind of a two-step problem because this function is broken in 2 places. What 2 places? -1 and 3. So you've got to have the limit as x goes to -1 from the left equals the limit as x goes to -1 from the right. And you have to have the limit as x goes to 3 from the left equals the limit as x goes to 3 from the right. Okay, so if you go at -1 from the left, which part of the function do you use? The top, the 4. And for the right, if you get close to -1, but you're a bit bigger than -1, which part do you use? The bottom or the middle? The middle. So ax plus b. And the first one's just going to be 4 equals -a plus b. Is that okay? All right. How about the next one with 3 from the left? You're close to, but a teensy bit less than 3. Which part of the function do you use there? The middle. Ax plus b. And for the other part, if you're a little bit bigger than 3, you use the bottom one, on the right side of 3. So that's 3a plus b equals -2. Can you put that information together to get what a and b should be? Do you see what I mean? There's this thing called substitution. Have you heard of it? Maybe? Okay. B equals 4 plus a. Take that. Plug it in for b. So 3a plus 4 plus a equals -2. So I think that's going to give you 4a equals -6, right?
Mm-hmm.
So a is -6/4, or a is -3/2. Do you agree with my mathing? Sorry, my negative went off the page, so sorry. And then knowing that, how could you find b? So b would equal 4 plus negative 3 over 2, which is 8 over 2 minus 3 over 2, so b is 5/2, right? And as a picture, this is two horizontal lines joined by a line with an angle with a slope that's not 0, right? Okay. One more example that's a little bit different than the previous ones. So these two examples we've done have been piecewise functions, right? There's two pieces that are joined together. This next one's also kind of a piecewise function, but a little bit different than a piecewise function because there's only one problematic point with that first thing. Does that make sense? So the question is what number should you have plugged in? So this is kind of like the question of if you have a line with a hole in it, what number should be plugged in there? Does that make sense? So the way to figure out what number should be plugged in there, it's asking like what should the y be, you find the limit as x goes to -1 of x to the 4th minus 1 over x plus 1. And whatever that limit equals is what you should plug in to fill in that hole. And this kind of reviews the stuff from section 2.3, which is good because you've got a test on it. So can you factor x to the 4th minus 1? Is it that cube thing or is it a difference of squares thing? Difference of squares. X squared plus 1, x squared minus 1 over x plus 1. And x squared minus 1 factors further into x minus 1, x plus 1. If you can do that factoring in one step, I'm totally fine with that. And now can you cancel the problematic denominator? Okay. Limit x goes to -1, x squared plus 1, x minus 1. And now can you plug -1 in? Yes, you'll get, I believe, 2 times -2, right?
Yeah.
Which is -4. So b should equal -4. And in that case, you will make this function continuous. The way that question is asked on WebAssign is phrased a little bit differently. What they're going to do is they're going to give you this part, and they're going to say, how do you make it continuous? Which is the same thing as asking, what should that value be? It's just the value you get when you take the limit, that's all. Okay. I'm actually going to finish the lesson in an hour. Ooh, victory. All right. The last thing in this section is something called the intermediate value theorem. And this theorem is pretty intuitive. Proving it's a little bit difficult, but we're not going to do that. We're just going to talk about what it means and how to use it. So suppose that you have a continuous function on a closed interval from a to b, and you have some number n between f of a and f of b. F of a and f of b are the y's you get when you plug in a and b. Does that make sense? Okay. And they can't be equal, and that is the y's are not equal. And what this says is there is a number c in between your a and b where when you plug c in, you get that n. The best way to understand this is with a picture. So here's the picture. You have a, you have b. Does f of a have to be less than or greater than f of b? It doesn't specify, does it? So I could draw f of a up there and f of b down here. Nothing specifies that they have to be positive either. So, I mean, one could go below the y-axis or they could both be below the y-axis. The number n, where does it live? Between f of a and f of b. So on the y-axis, somewhere in there is my number n. I'm going to draw a horizontal line at n. Okay. And my function is continuous. So I have to be able to go to from where f of a is to where f of b is without picking up my pencil, right? Can I get there without crossing my dotted line? No. So I have to cross the dotted line at least once, right? Could I cross it more than once? Yeah. So what this theorem says is that there is a number c where when you plug c in, you get out n. And what that is saying is that at that point where you cross the line y equals n, they're asking what x value did that come from? It's saying you can find an x, and when you plug that x in, you get out that y. That's the same thing as saying that your function has to cross that horizontal line. And, okay, f of a, f of b. You could have something like this. Way down there, and here's your n. You could do some kind of crazy like oscillation, right? In that case, I crossed it 3 times. This theorem doesn't tell you how many. It just says there must be at least one, meaning there could be more, but one or more places where you cross that line. If the function was not continuous, would this have to happen? So in other words, so here's an idea. If it was not continuous, the function that is, you could just have a hole there, right? So if it was not continuous, this thing is not true. And if the two functions were equal, if the two y's were equal, well then you could just have a horizontal straight line, and that's just kind of silly. Okay, this is commonly used to prove that a function has a 0. So you've got one value up above the x-axis, there's my f of a, one below, there's my f of b, and therefore my picture must cross someplace in between those two numbers. Okay, it's commonly used that n is 0. And to do this, you have to actually write like a little bit of a proof. Don't be scared because of geometry, okay? So here's a little bit of proof. So show that there is a root between 1 and 2. So sometimes you're going to be given numbers, and occasionally you've got to find those numbers yourself. But in this one, I told you what those numbers are. So every proof starts with the same word, let. When I was taught proofs, that was like if you knew nothing else, you could write let. I'm going to define a function, and the function is going to equal the thing that I have equal to 0. Okay, so let that f of x be this. And if you want to show this is equal to, this function equals 0, what you hope happens is that when you plug in one number, you get a positive. When you plug in one number, you get a negative. And therefore, the function is 0 in the middle by this theorem. So here's the next word. You say note, plug in 1. And I'm just going to tell you what you get when you do that. You get -1. And you plug in 2. And doing that, after much tedium, you get 12. I chose 1 and 2 because I was told it was in between 1 and 2. Okay? So here's your picture. At 1, is your function positive or negative? It's negative. At 2, it's positive. So somewhere in between there, function must equal 0, right? So you say, since f is continuous on the interval from 1 to 2, f of x must equal 0 between 1 and 2 by the intermediate value theorem, which is often abbreviated IVT. But you've got one number where you're negative, one number where you're positive, therefore your function must be 0 in between those two values. It doesn't tell you where specifically, but you could sort of like shrink your interval and do it again and shrink it and do it again. sort of figure out, and that's how you can approximate, one way to approximate zeros. Okay. So in that one, I told you what the numbers were. This next one, I don't tell you what the numbers are, do I? No, okay. So in the previous example, I had it equal to 0. Does it make sense that, so solving x squared equals 5 is the same as x squared minus 5 equals 0? Okay, so we're going to go with that instead to make it like the previous example. So what's going to be our function? Our f of x will equal x squared minus 5. In the previous example, I told you what numbers to plug in for x because I said between 1 and 2, right? If you want to show x squared minus 5 equals 0, you've got to find one number that when you plug it in, you get a negative. One number you plug in, another number you plug in, you get a positive. And you can pick different things. I tend to pick the things that are sort of whole numbers but as close together as possible.
4 and 6.
When plugging in both 4 and 6 give you both positives.
Oh, I'm so sorry. Yeah.
You're thinking, 1 and
3.
1 and 3.
Yeah.
Even better, how about 2 and 3? Does that make sense? But at 1 and 3 works, 0 and 3 works, it doesn't matter. So you say, note that f of 2 is negative 1, that's less than 0. And f of 3 is equal to 4, which is bigger than 0, right? It would have also worked to pick 1, it would have also worked to pick 0 instead of 2. But you've got one number when you plug it in as positive, one number you plug it in as negative. Since f of x is continuous on, what's my interval that we're talking about in this particular case? 2 to 3. F of x must equal 0 in parenthesis 2, 3, not at the end points because you know it's not 0 there. Oh, we'll add the by the IVT. If you would have picked 1 there, that would have changed those two different numbers. Does that make sense? Okay. So it's just a little proof. It's not super hard, right? Okay, so that's...
Should there be hard brackets around